In this video, we are going to start our discussion of section 14.7. This is triple integrals, but in other coordinates. So we're going to do cylindrical and we'll do spherical. The good thing is about this, it's all pretty straightforward, especially you guys are getting used to these, like looking at the regions and breaking them down. It doesn't go much past that. So here is a reminder of how rectangular works to cylindrical. The cylindrical, remember how we get our points is we have a r, which is the radius, which is this distance here. And then we also have a theta, which tells me the angle from the positive x-axis in the xy plane, how far it rotates out. And then z is just z. It stays the same. That z being the same thing is actually going to make this pretty straightforward for us. I'm going to go ahead, a reminder of this. This over here, sorry, this is in white. This thing here, we've brought it up a few times this semester. That just means the function in terms of x, y, and z, but with these up here, right? It's the same thing. It just means put the function in terms of that. So when we go from a normal triple integral over some region t, don't let that trip you up. I am going to my triple integral, and I'm going to do theta equals, and then it's going to be r equals and z equals. I'm going to leave them like that. And then inside of it, we have our function in terms of what we have there. So this is for cylindrical. All right, and then we introduce, it's an r, dz, dr, d theta. Just like the one before, or going to polar for double integrals, it's the same, like we're adding this r in. This is going to make sense of where that r comes from in section 14.8, so the next set of videos. So we have that. That is our formula. We just have to define our regions and take a look at what we have. So the first thing we're going to do is we're going to bound z. All right, to bound z, we have z is caught between two different functions. It could be values. We have this. This tells me it's bounded by the xy plane. And z equals 0 as well. Like we're bound in that first octant. So I know that z is bound between 0 and this function. Right? We also want to let z equal 0, just like last time. So z equals 0 gives me, if I look at my equation, I get 0 equals 4 minus x squared minus y squared. When we solve that to make it look like something we know, we get this. Hopefully you're like, that's a circle, right? We're getting so used to circles being everywhere within this stuff. So there's my attempt at a circle, corrected to an oval. There we go. Right, so this is a radius, a circle in the xy plane of radius 2. This allows us to take a look at a couple things. Okay, so now we're not going to have x or y, but we're going to have r. Well, I know that r squared is equal to x squared plus y squared, which means r is equal to 2. So I actually have from my bounds too. So here's my z, my r's. Okay, if I start here in the middle and go out, I know that r then is bounded between 0 and 2. And then taking a look at our circle, now remember it says first octant, so we're actually trapped for theta. Take a look at our xy, we are trapped in here. So that's between 0 and pi over 2. So now we have all our regions. So let's set that up. All right, so we have theta between 0 and 2 pi, or not 2 pi, sorry, wow. 0 and pi over 2. And we have r caught between 0 and 2. And then we also have z, which is caught between 0 and that function for minus. And then we want to put this in terms of r. So this is equal to 4 minus x squared plus y squared, which is equal to 4 minus r squared. All right, I replace y with its polar, r cosine theta. And then I get everything that was in there, r, dz, dr, d theta. All right. I'm going to work, I think in this first video, I'm going to work most of one integral out. And then actually for the rest of the section, we're not going to be working these out because I don't want to use your time. I think I have one more that we'll do. But for the most time, it's going to be set up. For this one, we're actually going to solve. So I'm going to rewrite this. Theta equals 0 to pi over 2. r equals 0 to 2, and I'm going to go ahead, that's just, it's in terms of z, so I get r squared cosine theta, z running from z equals 0 to 4 minus r squared, and then I got dr d theta. So plugging all this in, I'm going to rewrite. All right, and then we can plug those in, and they're going into z. So we're going to get r squared cosine theta times 4 minus r squared, and then the z equals 0 is just going to make them go away. So now we're going to work this out and jump to my next page. All right, I'm going to multiply all that out, I believe. That's what I want to do with that. Oh, I made a mistake back here. This cosine should be a sine. I'm glad I caught that. Sorry, you guys. So remember that y is r sine theta. All right, so this is a sine theta. There we go. Sorry, I was looking at my notes, and I'm like, it's not matching. All right, so I go from there, and I'm going to just put my r's together. So equals, okay, theta equals 0 to pi over 2, r equals 0 to 2, and then I'm just going to put these together. So I got sine theta times 4r squared minus r to the 4th, dr d theta. All right, I know the sign can just go out if I wanted to. I guess I can do that. Theta equals 0 to pi over 2, sine theta, because it's not r, and that's from r. We can go ahead and take our integral. We're just going to have this left inside. So that is 4 over 3 r to the 3rd minus 1 over 5 r to the 5th. And those are ran between r equals 0 and 2. And then I got d theta. There we go. We took the integral. Now I'm going to plug them in. We get theta equals 0, pi over 2. And sine of theta, and I'm going to plug all this in. I got 4/3 times 2 cubed minus 1/5 times 2 to the 5th. All that ends up being 64 over 15. So I'm going to pull that out front. And now I have this last integral here. Theta equals 0 to pi over 2 of just sine theta, d theta. 64 over 65. The constant stays. The derivative of sine is negative cosine theta. And that's ran from 0, theta equals 0 to pi over 2. Right? This turns out to be a 1 inside. So we end up getting 64 over 65. All right. I'm going to set up another one of these, and then we'll actually be going on to the other coordinate system. This is just cylindrical. Nothing changed really, except for we have that z at the beginning. But if we look at z, really this z just spits out a top minus bottom. But it's the same way. We're going to bound z, right? Convert to polar like we did. Then we let z equal 0. That gave me my xy plane, and that's how I can define r and theta. And then I set it all up. Okay, I'm going to do one more in this video. Right, find the volume of T, and T is the solid bound by that. That is a sphere. And then we have that. This is just another, I think this is going to be some paraboloid or something like that. We'll leave it alone. All right, so let's set up our boundary. What I'm going to do is we're trying to find Z, right? Get some kind of where does z range from here to here? And that's the problem, is they didn't give us the function above and below. Maybe they did there, bound by those two, but they're not set equal to z. I need to find a way to get z equals and figure out the bound. Now, I could set them equal to z and solve, but notice that this and that are the same. So I'm just going to plug that in. I got 8z plus z squared equals 9. If I shuffle all that around and minus the 9 over, I got that. This factors. I'm not going to spend video time factoring it. It is z minus 1 and z plus 9. All right, that spits out two values, z equals 1 and z equals negative 9. Now, z in this case, it doesn't make sense to call it a negative 9, and the reason being, think about plugging it into here. Into here, if I plugged in a negative 9, I have negative 72. equals x squared plus y squared. That's never going to happen, right? The right side, this side, always spits out positive numbers. It's never going to be the negative 9, but it could be z equals 1. Well, z equals 1, right? If I replace what z was equal to, all right, well, if I take this and solve for z, z is equal to 1/8 x squared plus y squared. So if I set that equal here, okay, 1/8, I'm going here, x squared plus y squared, that's what z is equal to 1. And I keep solving, okay, x squared plus y squared equals 8, right? That's multiplying both sides by 8. So this is a circle with radius of square root of 8. That is 2 square roots of 2. All right, so I know that my r is going to be, I have that circle, x squared plus y squared equals 8 with that radius, 2 square roots of 2. And I get a circle here. All right, close enough. And I know that the circle has that radius. So I'm going to set up my let's try to bound everything actually first. So z is between, right? I know it's 0 to 1, or sorry, 0 to 2 square roots of 2. That's from here, right? This is my, if I look at this plane, this is my xy plane. All right, and I know z is caught between those. Actually, z is going to be in between my two functions. Okay, I have the top function. So we have this. Let's actually go back here. Z is not caught between these two. Z is going to be caught between this function and that function. I just got to determine what those functions are. Okay, well, if I solve for this one, I have z squared equals 9 minus x squared minus y squared, right, which is just a square root. All right, so I get, if I change this to polar, I get the square root of 9 minus r squared. That's the top for z. And then the other one is already solved for z right here. I just got to determine which one is on top and which one is on bottom. So we have those two. Let me erase the two circles there. Those are top and bottom. How I can tell where to put them, and we could go a step further here. This is equal to 1/8 r squared. All right, so we have those two. Those are my z's. And how I can determine which one's on top and which is on bottom is I pick a point in this section right here, right, in that circle. Well, 0, 0 is in that point. If I plug 0, 0 into each one, I get 9 out of this one, right? And I'm thinking this right here. Plugging 0, 0 in there, I get square root of 9, which is 3. If I plug 0, 0 into this one, I get 0. So the top one is here, and the bottom is here. All right, so let's set this up. So the volume, I got my triple integral. I got theta equals, r equals, and z equals. Z is caught between 1/8 r squared and square root of 9 minus r squared. I have this picture to help me with r here. R is between 0 and 2 root 2. And then theta goes all the way around. I got 0 to 2 pi. All right. Inside my argument, it's volume, so it's just a 1. And then I get r dz, dr, d theta. This, if you want to work this out in practice, I'm going to keep it short for video's sake. This answer is 40 pi over 3. Please work that out and double check. The important part for this, and really going forward, a lot of this after this next section will be setups. We have 2 more sections that are some work where you got to validate things, and then other sections are going to be nice, easy setups solving these triple integrals or double integrals, depending on which section we're doing. All right, so this is the beginning of 14.7. We are going to, in the next video, focus on spherical. This is cylindrical coordinates.